Welcome everyone to this section of the course on data distributions. In this section, we're going to be exploring concepts that allow us to better understand different distributions of data. Recall our discussions of data visualizations and specifically histograms earlier in the course. You should notice that this is actually a visualization of how this particular dataset is distributed. So we can almost think of it as modeling the distribution of the data itself. For example, I can see the distribution of the total bill from the TIPS dataset that we've been exploring. This allows me to realize that most of the values are going to fall between $10 and $30, meaning that if I were to randomly pick a bill value, it has a higher likelihood of falling between $10 and $30 than being above $45. When thinking about our real-world datasets, we can use data distributions to model outcomes, depending on how the data itself is actually distributed. In this section, we're going to be exploring how to understand distributions and some different types of common distributions. So we're going to start off with some higher level ideas behind data distributions, including probability mass functions and discrete uniform distribution as an example of a PMF or probability mass function. And then we'll discuss probability density functions and the continuous uniform distribution as an example of a PDF or probability density function. Then we'll also talk about cumulative distribution functions. After that, we'll take a quick tour of some specific distributions like binomial distribution, Bernoulli distribution, and Poisson distribution. As you encounter real-world datasets, you're going to begin to see behavior and patterns in the distribution of the data that are actually common characteristics to a particular data distribution. Matching a real-world dataset to a particular distribution, that is some theoretical mathematical model, can actually be a very powerful tool. For example, understanding that certain datasets in the real world, such as the heights of people, are normally distributed allows you to apply statistical operations related to normal distributions. As a quick note, we actually cover normal distributions, otherwise known as Gaussian distributions, in the next section because it's actually a very specific and important distribution that shows up a lot in real life. So another example could be the binomial distribution, which can help you model events in which you have a sequence of independent event outcomes. For example, that could be used by a casino to model out the probability of winning on games such as blackjack or baccarat, which could help the casino itself manage expectations of future revenues from certain tables. Before we dive deeper into data distribution, let's give you an intuition of how to think about data distributions, especially the differences between probability mass functions and probability density functions, which are often confusing to beginners talking about data distributions. Let's begin with probability mass functions, otherwise known as PMFs. Now, the formal definition of a probability mass function is, quote, a function that gives the probability that a discrete random variable is exactly equal to some value. Now, that's a lot of words. And this definition can seem very intimidating and confusing at first glance. But let's break it down and we'll realize it's actually pretty straightforward and it unlocks a lot of potential use cases for us. Let's start off with that very last word, function. A function simply takes an input and then applies some transformation and returns the output. For example, I could define a function as f of x, where x is what you pass into the function. And I could define it as f of x is equal to x plus 1. That's a simple function that simply adds 1 to the input x, so that f of 2 is equal to 3, because 2 plus 1 is equal to 3. Hopefully you already realized that and knew the definition of that sort of function. That means a probability function is similar, except it's going to return a probability value. For a probability mass function, it returns the probability that a discrete random variable is exactly equal to some value. Let's dive into that idea a little further. This means a probability mass function can be written as the following. F of x is equal to the probability that x is equal to some particular value that is a particular probability value, where capital X is the discrete random variable and x is the certain value. So let's explore a simple example of a discrete random variable in order to fully understand probability mass functions. Imagine you are running a security test program on 100 employees, one of whom is the CEO. The security test program is going to send a test phishing email to one random employee out of the 100 total employees. The question arises, what is the probability that the CEO is going to be the one to receive the test phishing email? Now you can kind of figure this out in your head, but I want to frame it in terms of probability mass functions. Again, notice a few distinct features of the situation. There are a discrete number of employees, 100. And we should also mention they're discrete because there's really no employees between two employees. So if you have employee Bob and employee Cindy, there's no employee value that's between Bob and Cindy. Thus, they're discrete. And you have 100 separate employees. We're also interested in the probability of a particular event outcome. So the discrete number of employees gives you an idea that it should be probability mass instead of probability density, which will be for continuous situations, which we'll talk about later on. And again, we're interested in the probability of a particular event outcome, where the phishing email happens to go specifically to the CEO. This means we have a probability mass function. I'm looking for f of x as my function, where it's going to be the probability that x is equal to a particular value. In this case, I'm looking for the probability that x is equal to CEO. Essentially, what's the probability that this particular event of sending the email happens to go to the CEO? If we know there are only 100 employees and they all have an equal or uniform chance of being picked, then the odds of picking the CEO, that is, what's the probability that x happens to be equal to the CEO, are simply 1 out of 100, or 0.01 or 1% chance of picking the CEO. Which kind of makes sense. You probably already knew in your head that if you're going to have an equal chance of picking any employee, and only one of them is the CEO, then your chances are 1 over n, or 1 over 100. And in this case, since the outcomes were discrete, again, we label this as a probability mass function. It is the discrete outcomes that allow us to model this as a mass function. And in this particular case, we had what's known as a discrete uniform distribution. Keep in mind that's not always the case. For example, maybe the CEO could have multiple emails because he or she is so important. And in that case, maybe it's not going to be uniform because the CEO actually has a higher chance of being picked. But in this case, we kept it discrete uniform. When visualizing probability mass functions, you're going to see a distinct probability points for each outcome. For example, if we only had 10 employees with equal chances of being chosen, what would the PMF distribution visual look like? Well, the probability mass function for 10 employees with a uniform chance could be visualized as the following. Here, we're looking at a visualization of the PMF for the case where there's only 10 employees. So, keep a note here that there's no line connecting each particular employee. That's because each employee is discrete. Employee number 1 and employee number 2, 3, and so on. There is no employee 2.5. And then on the y-axis, I can see the probability of picking the employee, which happens to be equal to 1 over n, or 1 over 10, which is the same thing as 0.1. So what about probability density functions? So what happens in situations where the outcomes are not discrete? For example, instances where the outcomes are continuous. In this particular case, that means we're dealing with a probability density function. The formal definition of a probability density function is the following. A function whose value at any given sample in the sample space can be interpreted as providing a relative likelihood that the value of the random variable would be close to that sample. Holy smokes, that's a lot. So again, let's break it down. This appears actually kind of similar to the PMF definition, but the key difference is that we're looking and working with a continuous random variable instead of what's known as a discrete random variable. This requires a small shift in our mindset. Imagine that we're going to now send out the test phishing emails to multiple accounts using a third-party service. Typically, once we hit send, the emails are sent out within 1 to 3 minutes after we actually push the button. Note how we're now framing this problem differently. It's now actually a continuous random variable if we're thinking about the question, how long after I hit send will the phishing email actually take to go out to the person. So now I'm not even thinking about who's the phishing email going to hit. Instead, I'm thinking about the question, after you hit send, how long does it take for the email to actually reach the inbox? So for example, what's the probability of having the email go out over 60 seconds long? So again, what if we wanted to know the probability that the emails get sent at exactly the 1 minute mark? And I want to be very clear. When I say exactly 1 minute, I mean precisely exactly 1 minute. So 60.000000 seconds, etc., after we hit send. What you should be thinking about is, does that question even make sense? It's probably almost impossible that using this third-party provider, the email I sent is going to be sent at exactly 60.0000 seconds, etc. And the reason for that is because we're now dealing with a continuous feature or a continuous random variable. Because now we're dealing with time instead of the separate discrete employees, I now have a continuous random variable. That is, could be 60 seconds, 61, 62, and there actually are values in between 2 points in that random variable. There are values between 60 seconds and 61 seconds, and there's kind of an infinite amount of values if I keep getting precise enough. Hopefully you remember that from our discussions of continuous features. So for continuous random variables, we switch our thinking from exact outcomes, which we did for discrete random variables like exactly employee number 1 or exactly the CEO, to either approximations or interval ranges, since those make way more sense for continuous random variables, thus the term the density function. And if you go back to the original definition, that's why it said close to or approximate a certain value. So we're not looking for an exact match to a discrete outcome. Instead, it starts making a lot more sense for continuous random variables to talk about ranges or intervals. For example, it'd be more useful to know what's the probability that the time it takes to send the email is less than 1 minute. So this allows us again to answer the question, what's the probability that emails are sent out in 1 minute or less? And now I'm dealing with a range or an interval. And that makes a lot more sense for a continuous random variable. Thus, we can think about it as a probability density function. There are many different types of probability density functions, such as a normal distribution or something like a Boltzmann distribution. In fact, there are actually so many different types of distributions, both probability mass functions and probability density functions, you can actually view a list of them on Wikipedia. And I would encourage you to visit this link or just Google search list of probability distributions on Wikipedia and check them all out and explore them, maybe be even a little confused by them, but then understand that they're actually all just examples of either a PMF or a PDF. And we're going to dive into a few of them in this particular section of the course. The key insight for understanding data distributions is that once you can actually connect a real-world set of events or data points to a particular data distribution, you can leverage the properties of that data distribution to calculate probabilities. For example, in the very first example that I just talked about in this lecture, with probability mass functions and security phishing emails, I had 100 employees, all with an equal chance of being picked. That's my real-world situation. If I think about the theoretical match to it, it's actually a discrete uniform distribution. It's discrete because all the employees were discrete, and it's uniform since they all had the same probability of being chosen. That means I can actually look up the properties of a discrete uniform distribution on something like Wikipedia. And then I'll realize that there's actually a bunch of formulas already defined. And in fact, a discrete uniform distribution has the property that the probability of a single discrete outcome is simply 1 over n, where n is the number of discrete event possibilities. Our example, n was equal to 100 employees. Thus, the CEO had a 1 over 100 probability of being picked. That can seem super obvious to anybody who doesn't even know what data distributions are, but as the data distributions get more complex, it becomes necessary to actually look up the formula. So again, a discrete uniform distribution is a simpler use case where 1 over n may have been obvious even if you didn't realize it was a discrete uniform distribution. But keep in mind, there are many real-world situations that match up to more complex data distributions, like a binomial distribution, trying to figure out the odds of winning a hand at blackjack or something like that. So calculating those event probabilities would be difficult without referencing prior works or proofs. So we want to make sure we take advantage of all the work mathematicians have already done for us in history. That way, we already can connect real-world data sets to theoretical data distributions, and then we can match up the properties. So again, fortunately for us, mathematicians of the past, such as Bernoulli, have already done the hard work for us. We can stand on their shoulders to quickly assess what formulas to use once we know the data distribution that we're actually working with. Let's continue exploring data distributions, as well as taking a deeper dive into the concepts such as PMFs and PDFs discussed in this lecture.